Why did the lightest particle in the universe acquire mass? The origin of neutrinos, modular symmetry, and the traces left by information. Even at this very moment, an unimaginable number of particles are passing through your body. They do not strike your skin. They are not stopped by your bones. They pass through the entire Earth as though nothing were there. Some of them were born deep inside the sun. Some emerged from stellar explosions billions of years ago. Others may have been wandering through space since the earliest moments of the universe. They are called neutrinos. Neutrinos exist, yet they leave almost no trace. They carry no electric charge. They barely interact with light, and they collide with matter only on extremely rare occasions. That is why, to detect them, scientists build enormous tanks deep underground or beneath mountains, waiting for a single faint flash produced by one rare interaction among countless passing particles. Neutrinos may be among the quietest inhabitants of the universe, and yet, paradoxically, this silent particle created one of the clearest cracks in the Standard Model, one of the greatest scientific theories of the 20th century. The Standard Model describes the fundamental particles of matter and the forces acting between them with extraordinary precision. It explains how electrons and quarks interact, how photons carry electromagnetic forces, how W and Z bosons mediate the weak interaction, and how particles acquire mass through their interaction with the Higgs field. But in the minimal Standard Model, neutrinos were supposed to have no mass. Nature rejected that prediction. Today we will explore why neutrinos, the lightest known massive particles, possess mass at all. We will examine why the Standard Model could not explain that mass, how modern physics is approaching the mystery beyond the Standard Model, and how a recent study combines A4 modular symmetry, the linear seesaw mechanism, and computational optimization to describe neutrino masses and mixing. Finally, we will consider a broader interpretation from the perspective of IG theory, the information gauge framework. Could neutrino mass be understood not simply as an isolated property inside a particle, but as a dynamical trace left by the way that particle is connected to other states, fields, and the informational structure of the universe? And if such an idea is more than philosophy, what experimental signatures should it leave behind? Neutrinos belong to the lepton family, just like electrons. There are three known types of neutrinos: the electron neutrino, the muon neutrino, and the tau neutrino. These names come from the way neutrinos participate in weak interactions alongside electrons, muons, and tau particles. For example, a neutrino produced together with an electron in a nuclear reaction is called an electron neutrino. But neutrinos possess a deeply strange property. A neutrino created as an electron neutrino may later be detected as a muon neutrino or a tau neutrino. This phenomenon is called neutrino oscillation. At first, the idea that a particle can change its type while traveling may sound bizarre. An electron does not normally fly through space and suddenly become a muon. To understand neutrino oscillation, we must recognize that neutrinos carry two different kinds of labels. The first is called flavor. Flavor tells us how a neutrino is produced and detected through the weak interaction. Electron neutrinos, muon neutrinos, and tau neutrinos are flavor states. The second label refers to mass. A neutrino traveling freely through space propagates as a combination of three mass eigenstates, each with a different mass. These two sets of states do not perfectly match. An electron neutrino is not a single particle state with one definite mass. Instead, it is a quantum superposition of three different mass states. The same is true of muon neutrinos and tau neutrinos. We can compare this to music. When we hear a chord on a piano, it may sound like one unified sound, but that chord contains several individual notes, each vibrating at a different frequency. As time passes, the phases of those notes evolve differently. When they are recombined, the result may sound like a different chord. Neutrino oscillation works in a similar way. At the moment of production, the neutrino may appear as the chord we call an electron neutrino. But inside that state are three mass components. As they travel, the three components accumulate phase at slightly different rates. When the neutrino is measured again after traveling a long distance, the components may recombine in such a way that it appears as a muon neutrino or a tau neutrino. This phenomenon has an unavoidable consequence. For the different mass states to accumulate different phases, their masses must not all be identical. If every neutrino had exactly the same mass, or if all of them were truly massless, no relative phase difference would develop in the required way. The observation of neutrino oscillation therefore means that at least two neutrinos have different masses, and that means neutrinos cannot all be massless. In the late 20th century, scientists discovered that fewer electron neutrinos were arriving from the Sun than theoretical models predicted. At first, they suspected that our understanding of the Sun might be wrong. Perhaps the theory of nuclear fusion inside the solar core was incomplete. But later experiments using enormous underground detectors showed that the missing neutrinos had not disappeared. They had transformed into other neutrino flavors. Nature had not destroyed the particles. It had changed the names by which we were able to recognize them. There is something philosophically profound in this. We often imagine that every being possesses a fixed identity. We assume that a name represents the thing itself. But for a neutrino, the name given at production is not its eternal essence. It is one way in which a particular interaction reads the particle. The being may be one, while the bases through which it is interpreted may be many. Why then did the Standard Model originally treat neutrinos as massless? Electrons and quarks possess both left-handed and right-handed components. Here, left and right do not refer simply to ordinary spatial directions. They describe the relationship between a particle's spin and its direction of motion. The Higgs field connects the left-handed and right-handed components of a particle. Through this interaction, particles such as electrons acquire mass. But the minimal Standard Model contains no right-handed neutrino. It contains only the left-handed neutrino that participates in the weak interaction. Without a right-handed partner, the Standard Model cannot construct the usual Dirac mass term for neutrinos in the same way that it does for electrons. The counterpart was missing from the theory. For that reason, the minimal Standard Model assigned neutrinos zero mass. But neutrino oscillation tells us that nature must contain additional degrees of freedom, such as right-handed neutrinos, or some entirely different mechanism of mass generation. And this is where the deeper mystery begins. Neutrino masses are not merely non-zero. They are astonishingly small compared with the masses of other elementary particles. Even the electron, the lightest electrically charged particle, is at least hundreds of thousands of times heavier than a neutrino. Why are neutrinos so exceptionally light? The Standard Model offers no explanation. There is another mystery. Are neutrinos and antineutrinos truly different particles? Or because neutrinos carry no electric charge, could a neutrino be its own antiparticle? Particles such as electrons, whose particles and antiparticles are distinct, are described as Dirac particles. If a neutrino is identical to its own antiparticle, it would be a Majorana particle. This distinction is not merely a matter of terminology. If neutrinos are Majorana particles, a quantity known as lepton number may not be absolutely conserved. Such lepton number violation could even be connected to one of the greatest cosmological mysteries, why the early universe left behind more matter than antimatter. We also do not yet know the exact ordering of the three neutrino masses. In the normal ordering, the third mass state is the heaviest. In the inverted ordering, the first and second states are relatively heavy, while the third is the lightest. Neutrino oscillation experiments measure differences between squared masses. They do not directly reveal the absolute mass of each neutrino. It is like knowing the height differences among three mountain peaks without knowing the absolute elevation of the mountain range above sea level. The Standard Model describes the grammar of nature with extraordinary accuracy, but the neutrino was discovered in a blank space within that grammar. Perhaps the edge of every apparently complete theory conceals a doorway to the next one. Modern physics has developed several approaches to explain neutrino mass. The most direct approach is to add right-handed neutrinos to the Standard Model. Then neutrinos could interact with the Higgs field and acquire Dirac masses, just as electrons do. But this creates another problem. To make neutrino masses as tiny as observations require, their coupling to the Higgs field would have to be extraordinarily small, far smaller than the corresponding couplings of other known particles. This is mathematically possible, but it does not explain why the coupling is so small. A second approach is to consider neutrinos as Majorana particles. Because neutrinos carry no electric charge, a neutrino may be able to act as its own antiparticle. In that case, a right-handed neutrino could possess an extremely large Majorana mass. The result would be a very light neutrino of the kind we observe. This is the famous seesaw mechanism. Imagine a seesaw in a playground. When one side becomes extremely heavy, the other side is pushed upward, or, in the analogy of mass scales, driven very low. The existence of an enormously heavy, hidden neutrino state can naturally make the observable active neutrino extremely light. In the conventional seesaw model, however, the heavy right-handed neutrino may lie at an energy scale far beyond the reach of present-day accelerators. That is why physicists also study modified constructions, such as the inverse seesaw and the linear seesaw. In these models, the heavy neutral states may exist at much lower energies. Instead of relying entirely on an unimaginably large mass scale, they use a very small lepton number violating term, or a weak mixing parameter, to suppress the active neutrino mass. The seesaw mechanism may explain why neutrino masses are small, but another question remains. Why do the three neutrinos mix in precisely the pattern we observe? Why do the mixing angles have their particular values? And why is neutrino mixing so different from quark mixing? To answer these questions, physicists have introduced flavor symmetries. Rather than treating the three generations of neutrinos as unrelated particles, flavor models place them inside a common symmetry structure. The paper we are discussing uses a discrete non-abelian symmetry called A4. The A4 group has a structure well suited to treating three objects as components of a single triplet. That is why it appears frequently in theories of three generations of leptons and neutrinos. Traditional A4 flavor models, however, face a challenge. They often require several new fields called flavons. The vacuum expectation values of these flavon fields must be aligned in very specific directions to generate the correct neutrino mass matrix. A small change in alignment can alter the predicted masses and mixing angles. This is known as the vacuum alignment problem. The modular symmetry approach used in this paper addresses the problem differently. Instead of treating Yukawa couplings as unrelated constants, it makes them modular forms, functions of a complex variable called t. The mathematics may sound abstract, but the central idea is compelling. The many couplings determining neutrino masses and mixing are not completely independent numbers. They can emerge together from a single hidden geometric position in modular space. Imagine a city. At first glance, its many roads may seem to have been designed independently, but the roads often follow older features of the landscape: mountains, rivers, coastlines, valleys, and historical boundaries. There are many roads, but behind them lies one geography. In this model, the masses and mixing patterns of the three neutrinos are similar. There are many Yukawa couplings and matrix elements, but behind them lies a position in modular space, represented by the complex modulus T. The paper combines this modular A4 structure with a linear seesaw mechanism. In addition to the active neutrinos of the standard model, the theory introduces three right-handed neutrinos, denoted NR, three additional neutral singlet states, denoted SL, and a singlet Wheaton field called R. The active neutrinos are connected indirectly to these hidden neutral states. One of the connecting terms is extremely small, so the resulting light neutrino masses are also extremely small. The essence of the model can therefore be summarized in one sentence. The linear seesaw suppresses the overall size of neutrino masses, while the A4 modular symmetry organizes their pattern of masses and mixing. But the parameter space of the theory remains complicated. To find solutions compatible with experimental data, the authors used a metaheuristic optimization method called the ILA algorithm. ILA divides candidate solutions into several groups and allows them to explore different regions of parameter space. It then integrates the knowledge found by those groups and performs a final refinement around the most promising solutions. It is similar to sending exploration teams into different regions, combining their maps, and then conducting a detailed investigation of the most likely location. The researchers used 200 candidate solutions and 600 iterations, and they performed 100 independent optimization runs for both normal and inverted neutrino mass ordering. This computational strategy was designed to identify regions in which the complicated neutrino mass matrix agrees with current oscillation data. But an important caution is necessary. The fact that the ILA algorithm found a very small objective function value does not prove that this model is the unique description of nature. Different combinations of parameters may produce similar observables, and the objective function used in this study is not the same as a conventional chi-squared likelihood analysis or a Bayesian posterior probability. The study identifies viable and highly accurate solutions. It does not eliminate every competing theory. What kind of neutrino world does the paper predict? For normal mass ordering, the optimized solution gives a first neutrino mass of about 3.9 millielectron volts, a second mass of about 9.5 millielectron volts, and a third mass of about 50.3 millielectron volts. The sum of the three masses is approximately 0.064 electron volts. In this case, there is a clear hierarchy between the lightest and heaviest mass states. For inverted ordering, the first and second masses are approximately 50.6 and 51.4 millielectron volts, while the third mass is much lighter, at about 7.3 millielectron volts. The total mass is approximately 0.109 electron volts. This is relatively close to the cosmological upper limit of 0.1 electron volts used in the paper. Therefore, If future cosmological observations reduce the allowed upper bound on the total neutrino mass, the inverted ordering solution of this model could face a strong test. The two mass orderings also produce very different predictions for neutrinoless double beta decay, an experimental process that could reveal whether neutrinos are Majorana particles. For normal ordering, the effective Majorana mass, predicted by the paper, is about 0.84 millielectron volts. That is extremely small. For inverted ordering, the effective mass is about 27.9 millielectron volts. In normal ordering, the quantum amplitudes associated with the different mass states largely cancel one another. In inverted ordering, the cancellation is less complete, leaving a larger signal that may be accessible to future experiments. This difference is significant. Normal ordering is relatively comfortable with cosmological mass limits, but its neutrinoless double beta decay signal may be extremely difficult to detect. Inverted ordering offers a stronger double beta decay signal, but it lies closer to cosmological constraints. Nature has not yet told us which path it has chosen. Now let us take one step further. The IG interpretation that follows is not a conclusion of the paper itself. The paper deals with A to 4 modular symmetry, the linear seesaw mechanism, and ILA optimization. IG, the information gauge framework, is an additional interpretive and theoretical extension. From an IG perspective, neutrino mass should not be reduced to the statement that a neutrino is heavy because it contains more information. That would be far too simplistic. Information quantity and physical mass should not be directly identified. A more careful interpretation is to view mass as a dynamical eigenvalue that emerges when we diagonalize a matrix describing the relationships among states and fields. In physics, mass is not merely a tiny stone stored inside a particle. Mass describes how the particle couples to fields and how its energy and momentum are related during motion. The IG perspective adds informational relationships to this picture. Neutrino mass may emerge as a dynamical eigenvalue generated by connections among active neutrinos, hidden right-handed neutrinos, additional singlet states, and possible information gauge degrees of freedom. Mass would then be not information itself, but an inertial trace left by informational relationships. Neutrino mixing can also be read in a new way. Electron, muon, and tau neutrinos form the basis in which weak interactions create and detect neutrinos. The three mass eigenstates form the basis in which neutrinos propagate and accumulate phase through space. The PMNS matrix acts as a translation table between these two languages. Neutrino oscillation occurs because the language of measurement and the language of propagation are not the same. Think of a human identity. A person may have one role within a family, another in society, and another within the private world of memory. These are not completely different people. They are different ways in which the same being appears inside different networks of relationship. A neutrino also has one name when it is created and another structure when it propagates. In the language of IG theory, flavor is the way a relationship reads the particle, while mass is the way the particle propagates dynamically. The small mass term in the linear seesaw can also be interpreted informationally. The light neutrino mass emerges from a very weak connection between the visible active neutrino sector and the hidden neutral sector. If that small connection vanished, the light neutrino mass could also vanish. The tiny mass of the neutrino could therefore be interpreted as the residual trace of an extremely weak informational connection between the visible lepton world and a hidden neutral sector. But this remains an interpretation unless it is supported by a precise mathematical theory. To become physics, it must be formulated through a gauge-invariant Lagrangian and produce independent experimental predictions. The most conservative IG extension would not replace the mass matrix of the paper. Instead, it would take the A4 modular linear seesaw mass matrix as the baseline and add a very small IG correction. Most of the observed neutrino masses and mixing would be explained by the original model. IG would be allowed to explain only the small, structured residuals that remain between theory and experiment. A stronger hypothesis could interpret the modulus as more than a mathematical parameter. It might represent an effective alignment state of flavor information. An information gauge field could then shift that position by a tiny amount. The neutrino masses, mixing angles, and CP phases might acquire extremely small dependencies on the informational environment. But this is not yet an established result. It is a possible starting point for a future model. If IG exists in nature, what should we observe? The first candidate is a small residual in the neutrino oscillation phase. Standard neutrino oscillation depends mainly on the ratio between travel distance and energy. If an IG field creates an additional phase during propagation, the oscillation probability might vary slightly with the surrounding environment, even under otherwise similar conditions. Different energy ranges might yield subtly inconsistent values of the mass squared differences. Experiments with the same ratio of distance to energy might show discrepancies that cannot be explained by the standard 3-neutrino framework. But a simple constant shift in neutrino mass would not be enough. Such a shift could simply be absorbed into the fitted mass parameters. A genuine IG signature would need a distinctive dependence on energy, distance, matter density, or another environmental variable. The second candidate is an inconsistency in the measured CP phase. The paper finds an optimized Dirac CP phase of about 308 degrees for normal ordering and about 271 degrees for inverted ordering. If IG produces an additional information-dependent phase, experiments using different baselines and energy ranges might infer slightly different effective values of CP violation. For example, when experiments such as Dune and Hyper-Kamiokande reach sufficient precision, they may find that a single constant CP phase cannot fit all energy bins and all baselines simultaneously. That would be an important clue. But ordinary matter effects, detector systematics, and non-standard neutrino interactions can produce similar behavior. IG would therefore need to predict a common pattern in energy and distance that distinguishes it from these alternatives. The third candidate is a triangular inconsistency among different measurements of neutrino mass. Oscillation experiments measure differences between squared masses. Beta decay experiments measure a weighted effective mass associated with the electron neutrino. Neutrino-less double beta decay measures an effective mass that depends not only on neutrino masses, but also on Majorana phases. Cosmology constrains the sum of neutrino masses through their influence on the formation of large-scale structure. If one standard neutrino mass spectrum is correct, these different measurements should all be mutually consistent. But suppose the mass inferred in the laboratory, the mass differences measured through oscillation, and the mass sum required by cosmology cannot be reconciled within one spectrum. That might indicate that neutrino effective mass depends on environment or that an unknown interaction is present. Such an inconsistency would not prove IG theory, but it would provide a reason to investigate IG and other forms of new physics. The fourth candidate is a systematic breakdown of modular correlations. In an A4 modular model, one complex modulus simultaneously determines several Yukawa couplings. As a result, the mixing angles, CP phases, and neutrino masses are correlated. If future precision measurements show that not just one observable, but several observables deviate together in a particular direction, that could indicate a common correction added to the pure modular mass matrix. For an IG signature, a single anomaly is less persuasive than one structured pattern shared across several observables. The fifth candidate is non-standard coherence loss. Neutrino oscillation is a quantum interference phenomenon among different mass states. If neutrinos interact weakly with an information gauge environment while propagating, the interference pattern might fade more rapidly than standard theory predicts. The oscillation amplitude could be reduced in particular energy ranges or decay abnormally with propagation distance. But ordinary wave packet separation and other decoherence models can also produce similar effects. IG theory would therefore need to predict exactly which flavor channels are affected, how the effect depends on energy, and how large the deviation should be. In science, a new theory is not chosen merely because its explanation is beautiful. It must make risky predictions that distinguish it from competing ideas. Only when a theory accepts the possibility of being proven wrong does it fully enter the domain of physics. Neutrinos possess almost no mass. They carry no electric charge. They rarely interact with matter. Yet because of this very faintness, neutrinos can travel out from the cores of stars, escape from supernova interiors, and carry information from the earliest universe. When other particles are absorbed or scattered, neutrinos pass through history. The standard model treated neutrinos as massless particles. But neutrino oscillation revealed that nature possesses a deeper structure. Modern physics approaches the mystery through right-handed neutrinos, Majorana masses, seesaw mechanisms, flavor symmetries, and modular geometry. The paper discussed here proposes a structure in which A4 modular symmetry organizes the pattern of neutrino masses and mixing. The linear seesaw makes those masses extremely small, and the ILA algorithm searches the complicated parameter space for solutions consistent with experiment. The IG perspective adds another question. Is mass an isolated property stored inside a particle, or does it emerge from the way a particle is connected to other states, fields, and the informational structure of the world? We often imagine that existence comes first and relationships come later. But modern physics sometimes suggests the opposite. Electric charge gains meaning through interaction with a gauge field. Spin reveals itself relative to a measurement axis. Neutrino flavor changes through the relationship and interference among mass states. Perhaps existence is not fully completed before relationship. Perhaps observable reality emerges through relationship. Neutrinos pass through us while leaving almost no trace. But the history of science teaches us that the loudest phenomena do not always reveal the deepest truths. Sometimes the faintest signal can transform our entire understanding of the world. If one day we fully understand where neutrino mass comes from, we will have learned more than the weight of a single particle. We may understand more deeply how symmetry is broken, how hidden structures become physical properties, and how relationships give rise to observable reality. And perhaps on that day, the neutrino will seem to whisper something to us. The deepest secrets of the universe are not hidden only in the heaviest things. They may also be hidden in what appears to be almost nothing. This is Thoth Same Physics.